All right, so we're going to look at our global wind belts. We're looking at how, what is the general motion of the air movement on Earth. Okay, that's what we're looking at with this particular model. Now, this is our Earth, and we're going to assume a few things at this point in time. The first thing that we're going to assume in this model is that there is no tilt to the Earth. Okay, so we're going to ignore that tilt. We do this because it just makes it a little bit easier for us to explain, and we'll add in the hard parts later on. We are also going to assume that we have an even surface. What I mean by that is this surface, we can assume that it's all water, we can assume that it's all land, it doesn't really matter. But what we're looking at is all of this is going to heat evenly. So we don't have a landmass over here heating up more than the water over here. So we're looking at an even heating all over our globe. And then we are also going to assume that there's no rotation. Okay, so we're going to ignore the fact that the Earth is rotating for just a minute. All right, so if we look at our globe, we're going to define a few points on our globe here. This is our 0 latitude line. This is our equator. Up here, of course, is our pole. This is the North Pole. So this is 90 degrees north. Down here, we have 90 degrees south. Okay, so we have our two poles. And then we have them marked off in 30-degree latitude lines. So this is 30 degrees north. This is 60 degrees north. This is 30 degrees south. And this is 60 degrees south. All right, so those are just latitude lines. And we're just going to assume that over here we've got our sun sending energy to our globe. All right, so if you look at our sun is going to be heating the equator a little bit more than it is anything north or south, because this is just a more direct, this is not an even surface, this is a curved surface. So so the sun coming in, the energy coming in, is going to hit more directly at the equator than it is anywhere else. So the sunlight coming in is going to be coming in at a more direct angle here than it is here. So you can kind of see that a little bit. If you've ever been outside in the springtime, when the sun starts to go down, you kind of get that. You know that the sun at a lower angle is going to be quite a bit less powerful than sun at a high angle. So we have a little bit different heating. So even though we have even surface heating, what we have is different angles coming in, so that's going to change our heating a little bit. So here at our equator, we have much more direct heating, so it's warmer. So we have a very warm area, and if we heat up the land, that will in turn heat up the air. So warm air, as we know, is going to expand, it's going to become less dense, and it's going to rise. So warm air rises. So there's a belt along the equator. So here we are, if we're standing on our little island here at our equator. Okay, so this is up, not north, but up. Okay, so we've got air moving up because it's warmer. Okay, this is convection. So the warm air is less dense, it rises and moves up in our atmosphere. Now keep in mind that this is a 3D representation. So if we're standing right here, the air is going to be moving toward us. So if we're standing over here, it's going to be moving this way. So this is a 3D thing going on here. We also know that if we have rising air, it forms a low pressure system. So all along the equator, we have a low pressure because of this rising air. So convection causes the air to rise. When we rise air from the surface, we get a low pressure system, and we have a whole belt of low pressure all along our equator. And so we call this the equatorial low. If you were to look at a satellite picture of the globe at pretty much any given time, what you will see is a band of clouds all the way around the equator, pretty much constantly. It's very cloudy there. And the reason that is this air is rising. And we know that warm air rises. As it rises, we form clouds. And so what we see is we see a lot of clouds along that area. All right, now it does keep rising, but there's a point in our atmosphere where it can't go any higher. So we hit that tropopause, and we just can't go any higher. And so what's going to happen is it's going to spread out. If you think of this as a garden hose, if you take a garden hose and spray it towards the ceiling, okay, what's going to happen to that water? It can't go through the ceiling, it's going to spread out. So some's going to go this way, some is going to go this way. Now we also know that as we go up in our atmosphere, the temperature drops. So as this warm air is rising, the temperature is dropping. As we move north and south along this area, it's colder, so that air mass is going to take on properties of the air around it, and it's going to cool as well. So now we're getting colder air, and if warm air rises, cold air sinks. So at some point, that air is going to cool enough, it's going to become more dense, and it's going to sink back. My arrows are terrible today. It's going to sink back to the surface. And this is pretty typical. Around 30 degrees north and 30 degrees south, we have sinking air. Now, sinking air forms high pressure systems. So we have a high pressure system here and a high pressure system here. These are what we call the subtropical highs. And we have one in the northern hemisphere, and we have one in the southern hemisphere. Okay, so we have two subtropical high pressure systems right at 30 degrees. Now, if you know anything about high pressure systems, think summertime. When you get really high pressure, it's very dry. You just don't have any clouds in the sky. That's a high pressure system. If you look on a globe, do you know what happens around 30 degrees north and 30 degrees south? You have a lot of deserts. The Sahara occurs at 30 degrees. The southwest United States occurs at 30 degrees. The outback occurs about 30 degrees. So right in that area. Now, of course, there are other things that affect climate, but this is a pretty big one. So we have sinking air. We have those subtropical high pressure systems along 30 degrees north and 30 degrees south. So we have our sinking air. The problem is it can't sink into the earth. The earth is solid and the air is fluid. And so when it gets back to the earth, it has to go somewhere. So some of it moves back to the south. Oops, some of it moves to the north. And the same thing happens here. Some of it moves back to the north. Some of it moves to the south. So what we get is we get air movement in a cell. We get a convection cell. We have this warm air rising, spreading out, cooling down, sinking, and spreading out again. We have this warm air rising, spreading out, cooling, sinking, and spreading out again. So we get a rotation in there. We have a cell of rotation, a convection cell of rotation, and we call these Hadley cells. Now keep in mind again, this is all over the earth. This isn't on the side of the earth. This is a belt all around the circle of the globe. So we have this air motion called those Hadley cells. Now let's look at our poles for a minute, because what do we know about our poles? Well, we have the sunlight coming in at a very low angle, and so we have very cold air. What does cold air do? Cold air sinks. So up here at the North Pole, we have sinking air, so we have a high pressure. Same thing happens down here at the Southern Hemisphere. Cold air sinks, forming a high pressure. These are called polar highs. What you might not know is that our poles, those are deserts as well. Those are considered deserts because you don't have a lot of moisture. You don't have a lot of moisture because of those high pressure systems. All right, now same thing that happened over here with our high pressure. This high pressure hits the earth. It's got to go somewhere. So in the northern hemisphere, it goes south. In the southern hemisphere, it goes north, and it just spreads out. Now what's kind of interesting is right here. We have air coming from the north and we have air coming from the south. That air is going to meet at this point right here. This is a convergence. So we have air converging, we have air meeting from the north and the south. Well, if you bring a whole bunch of stuff together, it's got to go somewhere, and it can't go down into the earth, so it's got to go up. So at 60 degrees north, we have a low pressure system. Oops, there it is, because we have rising air. Now keep in mind, we have the rising air here is a different reason for the rising air here. Here it's because it's convergence. Here it's because of convection. Those are two different things and two different reasons. So we have rising air. And just like it did here, this rising air is going to spread out and cool and sink back down. It's going to spread out and cool and sink back down. Same thing happens down here. We have rising air. We have a low pressure that's going to spread out, cool, sink, spread out, cool, sink. Now what do you notice here? We have another rotation. We have another convection cell. We have another Hadley cell. So this rising air forms another Hadley cell. The same thing happens down here. Okay, so we have 6 Hadley cells forming because of these high and low pressure systems. Now this low pressure is called the subpolar low. I forgot to tell you that. So is this one. So we have these high and these low pressure systems forming on Earth because of the heating and cooling at different points. All right, so how does this affect the wind? Well, what we're specifically worrying about is the surface wind. So we're looking at what is happening at the surface. So if we start here at our equator, the equator has air moving towards it. So if we look at this Hadley cell, we have air moving from this high pressure system to this low pressure system. So we have air moving from north to south, all along that belt. So between 30 degrees north and 0 degrees, we have surface air moving from this high pressure, the subtropical high, to the equatorial low, moving south. Now the opposite is happening here in the southern hemisphere. What we've got at our surface is air moving from this high pressure to this low pressure. So the air in the southern hemisphere, oh my gosh, is moving north. All right, so we have air moving towards the equator from these subtropical highs. Now between 30 and 60, if we look at our surface wind is moving from this high pressure to this low pressure. So it's actually moving towards the poles. Okay, in both situations, if we look at our surface wind is moving towards the pole. My arrows are terrible today. And then from our pole, we have this high pressure to this low pressure, so our polar air moves away from the poles. And then northern hemisphere, it's going to move south, and the southern hemisphere, it's going to move to the north. So these are our basic global wind belts. Now keep in mind that we have a few assumptions up here that are not true. This is an idealized model, and this really does help us explain what's going on at a basic level. But what we're really concerned about today is this whole no rotation thing, because we know that the Earth does rotate. Now the Earth rotates if you are looking down from the pole, from the North Pole, you are going to see a counter-clockwise rotation. So if you are in the space station and you are looking down directly on the North Pole, the Earth will appear to be rotating counterclockwise. It will be going this direction. Now, if you were to look on the southern pole, this is kind of cool. If you were to look down onto the southern pole, it looks like it's rotating clockwise. Let that sink in for a minute because that's kind of weird. We have the same rotation. Now, the Earth is all rotating in the same direction. It's all rotating this way, but you're talking about perspective here. If you're looking down from the North Pole, it looks like it has a counterclockwise. If you were looking from the the South Pole, it looks like it's moving clockwise. All right, so this rotation then has an effect on the wind. Winds are fluids. They are very easily deflected. Waters are fluid. It's really easy to move those fluids. And so the motion of the Earth, the rotation of the Earth, causes something called the Coriolis effect. You will also see it called the Coriolis force, but it is technically not a force. A good example is if you were to shoot a cannonball from the North Pole. Okay, if you're sitting on Earth, if you are looking at it, what you would see is the cannonball just moving south. Okay, it's just moving that way. However, if you were to look at it from space, the Earth is rotating out from under it. And so what it would appear to do would get deflected. Okay, it would appear that the Earth is rotating out from underneath it. And so what this does is this serves to deflect the winds. It serves to deflect the waters. So if we take, let's start with our subtropical highs because these are right side up. In the northern hemisphere, the Coriolis effect deflects fluids to the right. So if we've got our winds moving this way, imagine you walking along this arrow. If you get deflected to the right, now you're going this way. So originally our air was moving this way, but because of our rotation, now it's moving this way. So we have a wind belt that gets deflected to the right. So now this air appears to be coming out of the southwest. So if you're standing up here, this air now appears to be hitting you from the southwest. So we call these the prevailing westerlies. Okay. Now the same thing is going to happen here. The difference is in the southern hemisphere, things get deflected to the left. So as we are walking along, okay, again, imagine you walking along on this arrow, you are going to get deflected to the left. So the air is going to move this way. So the Coriolis effect is going to deflect that air. Again, if you are standing over here, it appears to be coming out of the northwest. So again, we call these the prevailing westerlies. All right. So we have this wind belt between 30 and 60, the prevailing westerlies. Now if we look at this belt here, between 30 and 0, here we are in our southern hemisphere. If we are walking along this arrow, we're going to get deflected to the left. And so if we're standing here on our island in the equator, the wind appears to be coming out of the southeast. In the northern hemisphere, it gets deflected to the right. So as we are walking down our arrow, we get deflected to the right. And if you're standing on our island, okay, this appears to be coming out of the northeast. These are called the trade winds. In both belts, these are called the trade winds. Okay. And then our last belt, if we come down here, we're walking along our arrow, we're in the southern hemisphere, so we get deflected to the left. So if we're standing on our island in the poles, we appear to have air coming out of the southeast. These are the polar easterlies. Same thing here, we're at the poles, we're walking along our arrow. The northern hemisphere gets deflected to the right. Okay, so we're walking this way, we're going to get deflected to our right. And again, looks like it's kind of coming out of the northeast, so again we're going to call these the polar easterlies. So those are your global wind belts. In general, in these areas, winds are going to come out of a specific direction. So if you are along here in the trade winds, in the southern hemisphere, they're going to come out of the southeast, come out of the northeast in the northern hemisphere. Okay, so this is a general prevailing wind. There are a lot of other things that go into what actually happens and where the wind comes from on a given day. But in general, this is the wind pattern